So let's use the fundamental counting principle to derive the equation for combinations. Let's just start by treating a combinations problem like it's a fundamental counting problem. So I've got 5 people, A, B, C, D, E, and I want to choose 2 of them. So if I was going to treat this like fundamental counting, I'm making 2 choices. Who's the first person? Who's the second person? If my group of 2 people is really going to be 2 people, I can't have the same person in both choices. So that means there's 5 choices for who could be my first person, and then only 4 choices for who could be my next person. So that implies that there are 20 possible groups of 2. But just intuitively, that seems like too many, and we can see why if we write them all out. So here they are. This column is the column where I chose A to go first as my first person. This is the column where B was my first choice, and C, and so on. My restriction here that the second person, there's only 4 choices, that's only restricting me to say that the person I choose second can't be the same person as I chose first. But it doesn't stop me from counting, let's say, this possibility twice. Because if I'm choosing A as my first person, there's nothing stopping me from choosing D as my second person. Or I'm also counting the possibility of choosing D as my first person and then A as my second person. So this way of counting the number of possibilities counts these 2 choices as separate possibilities. But if I only care about what 2 people I end up with, and I don't care about the order that they got chosen, then every single possible pair I've actually ended up with twice in this table, because there's 2 possible orderings that group could have been chosen in. So instead of 20, I've got to divide by the total number of ways that I could have chosen that group. We're hoping to find a general pattern here, so let's try another problem. Let's say there's 4 people. Oh, bye-bye, Mr. E. There's 4 people, A, B, C, D, and we're going to choose 3 of them to be in a group. So again, let's approach it the same way. If I'm choosing the first and the second and the third person for my group, there's 4 choices for the first person, and then 3 choices for the second, and 2 choices for the third. So that implies that there are, 24 possible groups. Again, that seems like too many. If you were just going to blindly follow the pattern from the last example, you might think, okay, let's divide by 3. But we always want to think carefully about what we're doing, so let's write out all the possibilities again. So here we go. This column is the column of all of the choices where A was my first person, and here's all the choices where B was my first person, and C and D. And then within each column, you can see a pattern. So in the column where B was my first person, here's both possible groups where A was my second person. Here's both possible groups where C was my second person, both possible groups where D was my second person, and so on. But remember, a lot of these groups, I'm choosing the same people in a different order. So let's see how many repetitions I've got. So the group ABC, where else does it happen? So the group ABC should be the same as the group ACB, because it's the same people. It should be the same as the group BAC, or BCA. It should be the same as the group CAB, or CBA. It should also be the same group, well, it's going to be none of those, because these all involve a person D. So it seems like there are 6 different ways of choosing those same 3 people. If you go through, I think you'll see that no matter what group you select, so like BDC, you'll end up finding 6 total ways of choosing that same group of people also. And that's not an accident, because there's 6 ways to order 3 things. Forget this problem, if I just asked you as a separate problem, how many different ways can we reorder 3 things? That's like asking how many permutations are there for 3 objects. And the answer is 3 factorial, which is the same thing as 6. So that's where this 6 comes from. It's because once we've chosen 3 people, there's 6 total ways of reordering those 3 people, and each of those ways is possible as one of our choices. So let's bring it on home. In the last problem, we divided by 2, not because we were choosing 2 people, but because there were 2 different orders that we could have chosen the 2 people in that are the same. Here, because we're choosing 3 people, there's 6 different orders that are the same, or 3 factorial. So if we were choosing 4 people, each group of 4, there would be 4 factorial different ways of reordering them, which means that we would be choosing the same group of 4 people in 4 factorial ways. So the lesson here is this fundamental counting principle way of thinking is going to tell us all of the different orders that we can select the 3 people in. And so we've got to divide by the number of different choices that count as the same for us. And because different orderings are going to count as the same for us, we just divide by the total different number of orderings. So let's now do it completely in general to rederive the original combinations form. So in a way, it's actually a very simple step from permutations. If you accept this equation for the number of permutations of r things chosen out of n, that's saying first choose r things, in our case people, and then list the total number of ways of putting those r choices in all their different orderings. We want to do that same thing, only we want to count all of the different reorderings as the same. So we'll divide by r factorial, because that's the number of ways of reordering our choices. And so we're left over with just the number of ways of choosing r people where the order doesn't matter, because we've divided all of the different orderings that are treated the same out. And if I was just going to algebraically rewrite this, that's the same thing as n factorial over r factorial times n minus r factorial, which was the equation for combinations for n choose r. So that's it. It's a very simple short step.